Okay, this is Unit 3, Electric Potential, and I'm going to do problem number 3. Refer to Unit 2 and write the expressions for the electric fields due to the following charge distributions. So this is basically just copying over the formulas that we found for the E field in the previous unit. So for 3I, this is basically what it looks like. This is a long positive wire. It is charged with positive lambda, and the E field is away from positive, and these pink arrows represent the E field. And it's from this point, a distance r away. So just copying from the previous unit, we found that E equals lambda over 2 pi epsilon r, and that direction is outward or away from the positive. Okay, 2i, the E at a distance r from a large uniformly charged sheet having a charge area negative sigma. So this is basically what that looks like. This is a negatively charged sheet, as you can see the little negatives, and the E field is directed towards it because E field goes towards negative and away from positive. So it's towards it in both the top and the bottom, and it's negative sigma, and it's at a point up here, r away, could be wherever, but it's just r away from the sheet. And also copying just from Unit 2, our formula is E equals sigma over 2 epsilon, and it's directed towards the sheet because it's a negatively charged sheet. And part 3ii is E at a point between two large parallel uniformly charged sheets having equal but opposite charge area sigma. That looks like this. I just drew them parallel, one above and one below. I just put the negative on top. You can put them wherever, it doesn't specify, but I just put my negatively charged plate on top and the positively charged plate on the bottom. So my E field is directed upwards towards the negative and away from the positive, and it's at a point in between the two charged plates. And copying from Unit 2, our formula is E equals sigma over epsilon, and that's towards the negative sheet and away from the positive sheet, so just the pink lines. Okay, so that's part 3i, double I, and triple I. Now let's do part 3a. So part 3a says, use the integral change in v equals negative integral of E dot ds to find the potential difference between 2 points A and B having perpendicular distances A and B, respectively, from the wire in I, that's this, where A is greater than B. Which point is at the higher potential? So first we want to find our formula for the change in V. Well, actually, first we're going to draw a picture. So this is our picture. This is your positively charged wire, and the E field is away from it. And this is point A. It's greater distance away from the wire than point B. So distance from the wire to A is little a, and distance from the wire to B is little b. Alright, so now we're going to use the formula they gave us. Change in V equals integral of E dot ds. And we're just going to plug in what we found in 3i. So our E is lambda over 2 pi epsilon r dr. For this, ds and dr are pretty much the same thing because it's just the distance from the wire to the point. So we're just going to say that ds is the same thing as dr, so our integral is a lot easier. And that integral is from A to B. Alright, so I'm just going to bring the constants out front so the integral is easier. So our constants are lambda over 2 pi epsilon, and then it's times the integral from A to B of 1 over r dr is all you have left. So it's a super easy integral. It's just the ln r, because it's 1 over r, integral of 1 over r is ln r, and that is from A to B, and our constants are still out front. And then, so you plug in A and B in your integral, and then you just end up getting negative 2k lambda ln of b over a, because ln of b minus ln of a is ln of b over a. It's like a rule thing. And we put k because k is 1 over 4 pi epsilon, so it has to be 2k in order for the 4 here and the 2 to cancel out. So it's 2k lambda ln of b over a. And it's negative because you're going in the opposite direction of the E field. So you're going from A to B, which is the opposite direction of the E field, so it's going to be negative. Okay, part B. Oh, sorry, one more thing. It asks which point is at the higher potential. So it's actually higher at point B because you're going from A to B, and the E field is away, so the opposite direction, so it's actually higher at point B. So, part B. It says, do the same for double I, where A and B are perpendicular distances from the sheet. So, this is just the picture I drew. So this is our negatively charged sheet, and the E field is towards the sheet in both directions, up and down. And I just drew A and B on top so it's easier to see, but you can draw it wherever you want. But A has to be longer than B, so A is above B, and the distance from the sheet to A is A, and the distance from the sheet to B is B. And it's negative sigma. So we're just going to start with the integral. Change in V is integral of E dot ds, and then you're just going to plug in the formula that we got. So it's from A to B, and it's sigma over 2 epsilon, but since our charge density is negative for the sheet, we have to use absolute value of sigma, because we're going to do direction at the end, so we don't want the negative to mess up our when we plug in for the integral. So we're just going to put absolute value around it, and again ds is the same as dr. So I'm going to bring my constants out front, which is absolute value of sigma over 2 epsilon, and then integral of A to B of dr. So everything cancels out and you just have dr, so that's super easy integral. Once again, it's just r, so you plug that in, so it's b minus a, and then you get 2 pi k absolute value of sigma times b minus a, because k is 1 over 4 pi epsilon, as we said up here. So you can just plug that in and you get 2 pi k because it cancels out with the 4 pi on the bottom. So for part B, they also ask which point is at the higher potential. So for this one, the higher potential is actually point A, because the E field is the same direction that you're going, so it's going to have higher potential at point A than at point B. Okay, so that's A and B. Now on to part C. So it says, do the same for triple I, where A and B are perpendicular distances from the positive sheet. So this is the picture I drew for this. You can draw this a bunch of different ways. They could be, one could be here and one could be here. I mean, this could be negative, this could be positive. It doesn't matter, but it all comes out the same. So this is, I just drew the positive on the bottom, negative on the top, and your E field's going from the positive to the negative, always. And then it says measured from the positive. So I'm going to put my A from the positive, and it's going to be a distance of A away, little a. And then the B is below that because you're going from A to B. So that is a distance of B from the positive. Okay, so same thing as before. We're using our change in V equals integral of E dot ds. They gave that to us. And then we're just going to plug in the formula we got from 3 triple I, and that is sigma over epsilon. So same thing as part B. We're going to have to put absolute value over sigma because this sheet is negative sigma, and we don't want the negatives to get in the way because we're going to do direction at the end. So we're just going to put an absolute value around it, and that's from A to B. So taking the constants out front, that's sigma over epsilon, integral of A to B of dr, and it's super easy. Once again, it's just r, so you plug that in, and you get 4 pi k, absolute value of sigma times A minus B. And this one, it's higher at point B because you're going from A to B, so it's higher from point B because it's the opposite direction of the E field, because the pink lines are the E field and you're going the opposite direction. So it's higher at point B because it's closer. Okay, so the last section is part D, and it says, in each case, I, double I, and triple I, does a positive charge have higher potential energy at point A or point B? And what if the charge is negative? The positive charges move in the same direction as the E field, so the highest potential energy is at the same points as those stated above when we found the highest for the E field. It's the same for potential energy, so it still goes BAB for ABC. So A is at B is at point A, and C is at point B. And then for negative charges, it's the opposite because they move in the opposite direction of the E field. So they would be highest potential energy at the opposite point. So for part A, it would be at point A, and for part B, it would be at point B, and for part C, it would be at point A.